Hi everyone, my name is Abby. I'm a senior right now at Brown University studying computer science with a focus in security, and today I'll be presenting the reverse engineering workshop. So just an overview, kind of an outline of everything we're going to cover today, reverse engineering and the x86-64 overview, GDB, and then other debuggers that you can use for this as well. Then I'll go into an assembly overview, and specifically we'll talk about if statements in assembly and loops in assembly. So what is reverse engineering? So simply put, it's just deconstructing things kind of backwards, and it's a term that's often used in security. So just a quick assembly overview. So assembly is a low-level programming language. It can come from compiling higher level languages like C or C++, or it can also be written on its own. So right here, this picture is just an example of assembly code that you can kind of step through using a debugger like GDB, which I'll get into in a bit. So yeah. So just kind of another example to make everything more concrete. You can see here that we have a high-level programming language C with this swap function, and then the compiler will go and turn that into assembly, and then the assembler will turn that into binary machine language. So reverse engineering, going back to that, is something that we can apply to assembly. Say we're just given this assembly code to kind of like figure out what's going on, or maybe exploit some vulnerability in the software that we're looking at. So yeah, ultimately assembly is just a low-level programming language. So now I'll go into a GDB overview. So GDB is a debugger that will allow us to set breakpoints. I'll get into what a breakpoint is in a minute. But yeah, we'll go over some of the kind of basic GDB commands that you can use on assembly. Also, you can use radar2 as well. And so yeah. So the first GDB command is just compiling. So for instance, if we had like memsam.c and that was our source code, like our C program that we wanted to compile, we would compile it with the G flag. And yeah, so this is just kind of an example of that command. And then for invoking and quitting GDB, in order to invoke GDB, you just want to type GDB in the Unix terminal. And then to quit out of it, once you're already running a program and stepping through it, you just want to type Q. So the next command is this help command. This is super helpful in general for if you don't know how certain commands work. You can just type help and it will basically give you all commands with like how to run them and tell you what they do. So that's a super helpful one to remember. So then we have run. This just will start the actual program running within the GDB debugger. And then after that, we have break. So a breakpoint, like I was mentioning earlier, it's just a spot in our code where we might want to temporarily stop execution in order to check things like the values of variables. So maybe we're trying to break into something, or maybe we have a bug in our code. So that's super helpful. And so what we can do is we can set a breakpoint at a certain line within our code. And then maybe we want to see like the value of a variable at that line. So we can do that by typing something like break, and then you want like your file name and then your line number as well. So then after that, we have clear, and that will just delete the breakpoint that is set at a certain line number or function. So it can be called with the same exact parameters as break above. So you'll just get rid of that breakpoint if you have it there. So then we have continue. That will just keep our program running again after we've hit a breakpoint. So let's say I've hit a breakpoint, I print out the value of a variable, and then I want to keep my program executing. I'll just type continue. Then we have step, which will execute the current line that we're on, and then it will stop execution again before the next line that we are on. And then next will continue until the next source line in the current function. So this is similar to step, except for if the line that's about to be called is a function call, then that function call should be immediately executed, and we won't go into that and kind of go through it line by line. And then lastly, kind of an important one is just print. So that will print out the value of the expression that we're looking at. So like I was saying earlier, if we're stopped at a breakpoint and we want to print like a variable name at a breakpoint, you can use print. So you can do that also for like a list. This is an example here. And yeah, so those are some of the basic GDB commands that are helpful. So now I'll just get into a quick if statement overview. So just kind of I'll go over how if statements work in general in like higher level languages, and then we'll kind of go in and see what these look like in assembly. So for an if statement, we'll have some condition here, which will evaluate to true or false. If the condition evaluates to true, we'll go into this block. Otherwise, we might have another condition. We might have, 5 more after this, else if sort of blocks. If that's true, then do this. And then we'll have that last else, which says if none of these above conditions are true, just do this. So 2 of the main instructions that are used in assembly with respect to if statements are CMPQ, and that's like computing kind of A minus B without actually setting a destination. And then also test Q, and that's like, it's a bitwise operator which will compute A and B also without setting a destination. So now I'll quickly just go over jump in assembly. So jump instructions are used to transfer control to different instructions. And so there are different types of jumps. The last 2 values down here in this table, they refer to unsigned integers. So if you remember, unsigned integers can't be negative, while signed integers represent both positive and negative values. And that's how we do this because the computer needs a way to differentiate between the two. So it uses different methods to kind of interpret those. And then for signed integers, it uses something called the 2's complement representation. And then unsigned integers, it just uses normal like binary calculations. So after this slide, you can take a look at task 3 in this room. Okay, so now kind of going more into if statements with a little example. If you go into the if statement folder and you start R2 and then run a few commands, which you'll see in the room, we'll kind of see this here, which will analyze our program and list our functions and also disassemble our main function. So we can go ahead and we can set breakpoints on the JGE and the JMP instructions by referring to their hex addresses, which are right here, to know like the line or the instruction that we want to break on. So yeah, so once we've added these breakpoints to stop execution of the program when we get to these, we can kind of see the following. So you can run DC to start execution of the program, and it will start executing until our first breakpoint. So if we look at the first two lines, those are about pushing the frame pointer onto the stack and then saving it. This is the way that functions are actually called. And then the following three lines are assigning values 3 and 4 to our local arguments, which are var8h and var4h. And then those values will be, the value of var8h will be stored in our EAX register. And then we have our CMP1 instruction, which compares the value of EAX with that of the var-h argument. So to actually view the values of the registers, we can type in DR. So that's what this sort of screenshot is right here. So we can see the value of RAX, and this is a 64-bit version of EAX, and it contains 3. We saw that the JGE instruction is jumping based on whether the value of EAX is greater than var4h. And then to see what's in var4h, we can see at the top of the main function, it tells us the position of var4h. And so we can run a command to print what is in this RPB OX4, and it will show us the value 4. And then we know that EAX contains 3, like we already said, and 3 is not greater than 4, so our jump will not execute. And instead, it will just move on to the next instruction. So to check this, you can run DS, and it will go on to our next instruction. Next, we have RIP, which is the current instruction pointer, and it will move us on to the next instruction to show us that we're correct. And then the current instruction will then add 5 to var8h, which again is a local argument. So to see that this actually happens, you can check the value of var8h like we did before, and then you can run DS, and then you can check the same value again. And this will show us that it actually increments by 5. So then the next instruction is an unconditional jump, and it just jumps to clearing the EAX register. And then the pop queue instruction involves popping a value off the stack and reading it, and the return instruction sets this pop value to the current instruction pointer. So in this case, it shows the instruction of the program has been completed. And yeah, so to understand this a little bit better, how an if statement works, you can check the corresponding C file, which is in the same folder. Okay, so we have 2 types of loops in our sort of higher level programming language. The first one is while loops, and we'll have some condition like I discussed earlier, which if evaluated to true, it will keep going. Our while loop will continuously iterate. And then for our for loops, we'll have some value initialized. We'll have a condition which we want to stay in the loop if that value satisfies the condition. And then we'll change the value right here that's used in the condition. So for example, if we were iterating over an array, we might have I representing the index in our array. We might set that to 0, and we might say, well, I is less than the length of our array, increment I by 1, and then we might do some operation within our array. So now we can kind of look at how this might apply into some assembly by looking at some examples. So first, you can enter the loops folder and run R2 with the loops1 file. So again, this will analyze everything, disassemble the main function, and list the functions. So we can start by setting a breakpoint at this JMP instruction using the command db and then the address of the instruction. Doing this will allow us to skip those first few lines, and those we already talked about a bit with if statements, which is just kind of passing values to local arguments. So once we reach the breakpoint of our JMP instruction, you can run DS to move to the next instruction. And since this is an unconditional jump, meaning it will always happen, it will move to the CMPL instruction. So here we can see the CMPL instruction. It's trying to compare what's in the local argument var_ch with the value 8. So to see what's in var_ch, we can check the start of the disassembled function and check the memory. And in this case, that would be RBP0FC. And we can see here that it contains 4. And then our next instruction is JLE, which is right here. And that's going to check that the value var_ch is less than or equal to 8. And since 4 is less than 8, we'll jump to our next add1 instruction. And then the add1 instruction is going to just add 2 to the value of var_ch, and it will continue and go to the CMPL instruction. And then since 2 was added to var_ch will now contain 6. So we did 4 plus 2, and that's still less than 8. So we'll jump back to the add1 instruction, and this can be seen if we continue execution using DS. And so we can see that this is kind of a loop because we started off at 4, we added 2, that gave us 6. We're still less than 8, so we'll go back to add 1, add 2 again, and now we're at 8. So we can infer that the loop will be something like, while our variable ch is less than 8, increment the value of ch by 2. So an even faster way maybe to examine this would be to add a breakpoint at the CMPL instruction and run DC. And so since this is a loop, we'll always break at that CMPL instruction. And so now you can look at the loop 2 binary to answer some of those questions and also check out task 5. So that kind of concludes the assembly reverse engineering workshop. I hope you were able to learn a bit more about maybe assembly code and just reverse engineering in general.